Good evening, boys and girls. Welcome to another great lesson on Technical Sciences, grade 12. You are with me, Mr. Sibanyoni, and I'm so glad that you could join me for this particular lesson. And we are learning and we are preparing ourselves thoroughly for topics that are really important in Technical Sciences, grade 12, so that you are able to do well and you get your distinction in this subject at the end of the year. Without wasting any time, let us look at the outline of the lesson for today. So, we will be reverting back and quickly looking at what we are required to know as per the examination guidelines. Remember, there could be some of the learners that are joining us for the first time today, and we need to bring them to par with the rest of the content. And then in the features of the topic, we will be learning light, but we will be doing that through questions. Remember, we are preparing for the final examination, so we are doing more questions and questions and questions. And as well, I will be telling you and giving you more tips about how to prepare this section for the final examination and the mark allocation of this topic at the end of the year. Now, we quickly go into what we are required to know as per the examination guidelines. Now, my dear learners, you would know that during the course of the week, I highlighted this for you, and we have actually covered all the content on this particular topic, and hence we are actually just learning through doing questions. Now, these are the important definitions that we learned in this particular topic. Firstly, we learned how to define the term wave. And we said a wave is a disturbance that transfers energy through matter or space. And we know that definition is for 2 marks or nothing. So it is a disturbance and it does travel and transfers the energy through matter or space. Then we learned the definition of reflection, and we know that reflection is the change in direction of a wave upon striking the interface between 2 materials. I hope you remember this definition by now, because it actually encompasses what that reflection is and how does it happen. And then we have the definition for refraction as well. And with refraction, we say it is the bending of light altogether. So we don't confuse the 2 definitions. If it is reflection, it is the change in direction. If it is refraction, it is the bending of light. And this is when it passes from one medium to another. Now, very important, again, noting the differences between that reflection and refraction. Remember, with reflection, it is when it strikes the interface between 2 materials and it returns to the original medium. But when we deal with refraction, it bends, but it doesn't return to the original medium. It passes from one medium to another. So it moves from medium 1 to the second medium. It means it moves from the original medium to the next medium. So that is refraction, and that is the difference between the 2. Then we must know the definition of a critical angle. And number 1, we know that a critical angle, it is an angle of incidence, right? That is the first thing we know about a critical angle, is that it is an angle of incidence. Secondly, where is that angle of incidence? We know it is in the denser medium. And what does it do? We know if the angle is a critical angle, the refracted ray will pass through the surface of separation of the two media. And that is why we define critical angle as the angle of incidence in the denser medium such that the refracted ray just passes through the surface of separation of the two media. And then we have the term dispersion. And we know very well that dispersion is the phenomenon whereby light breaks up into its component colors. A very critical definition for you to know. Then we go further, and you are supposed to know how to discuss the following: the laws of reflection and the laws of refraction. And they are not stated there, but I gave you those laws, and there are 2 points to that. There are 2 laws to that reflection and 2 laws to that refraction. Perhaps as an icebreaker, let me give you a minute and see if you can refresh your memory before I give you the 2 laws, because you see here, they are not written down, and this is exactly how it looks in the examination guidelines. It just says, discuss the laws of reflection, discuss the laws of refraction, and we've done that extensively. So you have a minute. I want you to think about it, and just after a minute, I hope that you will be able to state the laws of reflection with me and the laws of refraction. Check if you can remember. I'm giving you 1 minute. Right. That is a minute, and you will recall that the laws of reflection, firstly, they talk about the relationship between the angle of incidence and the angle of reflection. Secondly, it talks about the normal, the incident ray, and the reflected ray altogether. So we start with the first one. The laws of reflection. First one says the angle of incidence is equal to the angle of reflection. Then we will give you 1 mark there. Secondly, it says the incident ray, the normal ray, and the reflected ray all lie in the same plane, and that will give you the 2nd mark. Then we go to the laws of refraction. You will remember there, my dear learners, that it will also encompass 2 points there, 2 of the laws that govern refraction. The first one is, it does talk about the relationship between the angle of incidence and now the angle of refraction. And then it talks about the incident ray, the normal, and the refracted ray. Now let us state it then. The first one, it tells us there is a relationship between the angle of incidence and the angle of refraction when the light ray passes through the boundary between the two media. The second one tells us the incident ray, the normal, and the refracted ray all lie on the same plane. And that one would give you the second mark. So please, my dear learners, know these 2 laws for each reflection, for each of reflection and refraction. And I have specifically given you this time to always, just see if you are able to remember and to check if you also know the important stuff. Then total internal reflection, you must know how to define it. And we know it is when the angle of incidence is greater than the critical angle. It has to be greater than the critical angle. All together. So remember this. You will get total internal reflection when the angle of incidence is greater than the critical angle. And then the ray of light reflects into the original medium. So I've highlighted that for you because you need to know that you can never have total internal reflection if the angle of incidence is not greater than the critical angle. Or rather, you cannot have total internal reflection if the angle of incidence is less than the critical angle. It has to be greater than the critical angle. And then you will have that total internal reflection. And because it is internal reflection, or because it is reflection, it means the ray of light reflects into the original medium. And therefore, the full definition will be, it is when the angle of incidence is greater than the critical angle, the ray of light reflects into the original medium. Secondly, you must be able to discuss conditions of total internal reflection. And you see, the first condition, you actually get it from this definition. Condition for total internal reflection simply says to us, or if they ask us about the conditions of total internal reflection, they are actually asking us what should happen or what are the requirements for total internal reflection to take place. And we know, firstly, the angle of incidence must be greater than the critical angle. Then I will get the first mark. Number 2, we know the light ray must be passing from an optically dense medium, from a more optically dense medium to a less optically dense medium, and never the other way around. And that will give you 2 marks. And then we must be able to state the uses of total internal reflecting prisms. And I said you must know at least 2 because we would ask you for at least 2 and not more than that. So total internal reflecting prisms. Number 1, we use them in optical fibers. Number 2, we use them in endoscopes altogether, and that is going to be 2 marks at least. Then the lenses. I said we must be able to discuss the frequency and wavelength of the various components of light altogether. So basically, we need to know the relationship between frequency and wavelength. Are we together? Right, and we know what that relationship is. And we'll talk more about that as well, because today we will be focusing on lenses again. Again, very important, we must be able to discuss and draw the transmission of light through a convex and a concave lens. Very important, my dear learners, we need to be able to do that. Now, this section, this bullet there, is the biggest focus again of today's lesson, because this is a high order question, it's a level 4 question, and it is definitely going to be there. We are most likely, 99% likely, going to ask you to make a drawing to show how light is transmitted through one of the two lenses, either a convex lens or a concave lens. And you must be able from that to tell us if an object is placed at a particular position, where is the image going to be formed and how is the image going to be? Meaning, what are the properties of that image? So this is essentially what the exam guidelines require of us, to be able to look at an object, the transmission of the light from the object, going through the convex lens or a concave lens up until an image is formed, and be able to discuss even the properties of that image. Then we must be able to discuss applications of convex and concave lenses. And then we must be able to give the properties of images formed by concave and convex lenses. So the image that forms through a concave or a convex lens, we must be able to give its properties. And furthermore, we must then be able to give the properties of the concave and the convex lens themselves, and not just the properties of the images. So this is essentially what we have learned. So I am saying to you, the biggest focus for today will be this, because I will be showing you how to draw the direction of light and the transmission of light through a convex as well as a concave lens, and how an image is produced and how to place your object and all of that all together, right? And after that, we will look at questions that are going to help you to do well in this section of the work. Now, let us look at a lens. Number one, this lens, there would be a convex lens. Now, a convex lens, we know, my dear learners, it looks like this, right? It looks somewhat like this. So there, it is just represented as a line altogether. But please, my dear learners, what I'm expecting you to do is to actually show it to me altogether in the form of a lens. So there, it is just shown as a line. I'm simply trying to just make it a little bit easier for you as well to see how the lines are moving. But you will draw it exactly as it looks here altogether. So I'll just do something like this for you. Right. This is somewhat a convex lens. It's quite skew, but you would know how to draw it accurately. Now, this position there, my dear learners, there, right in the middle of the lens, right in the middle of the lens, we refer to that as the optical center. This here is the optical center. Altogether, this is the optical center. And this position there is the focal point. So there we have your focal point, which is this point here. Altogether, this point there, we call it the focal point. This line here, my dear learners, remember we call it the principal axis. This is the principal axis. And then this line there, we call it the optical axis. Are we together? Good. Let's start again. This point here is the center of the lens. It is the optical center. This point there, which we label as F, we call it the focal point. This line here, this line all the way, this line all the way, we call it the principal axis. And then this line here, this one, we call it the optical axis. Now, my dear learners, this is a convex lens. And remember, a convex lens has various properties. Firstly, a convex lens, my dear learners, we know that it is converging in nature. It means it makes the light rays to meet altogether. It makes the light rays to meet. Again, we know here in the middle, it will be thicker than at the edges. Are we together? It will be thicker than at the edges. For example, the middle there will be thicker than the edges. And that is why we say those are properties of a convex lens. Now, a convex lens will give you the image of an object. So the object is what really exists, and the image is what is going to be seen. So let us say we take an object and we place it between F and 2F. Now, what is F and what is 2F? We said F is the focal point. 2F is 2 times the focal point. Now, how do we get F? Or how do we get 2F? Firstly, there, remember I said that is the optical center and that is the focal point. And yesterday I told you the distance from the optical center, which is this point, up to that point is the distance from the optical center to the focal point. And we call that the focal length. Altogether. Now, if the focal length is 10 centimeters, for example, meaning from the optical center to the focal point is 10 centimeters, it means from F to 2F, then it must be another 10 centimeters altogether, which then places 2F at 20 centimeters. In other words, if the focal point is 10 centimeters from the optical center, then 2F, which is twice F, it will be 2 times 10 centimeters. And this point must then be 20 centimeters from the optical center, or you simply say it must be 10 centimeters from F. So my dear learners, to put it simple for you, from the optical center to F, it's 10 centimeters. Then from F to 2F, you will measure another 10 centimeters. The same will apply on the other side of the lens. If from this point to F, it's 10 centimeters, then from this point to F must be 10 centimeters. From F to 2F, it must be 10 centimeters. So the focal length is 10 centimeters, the distance from the optical center to the focal point. Now, let us say we place an object between F and 2F. Now, if we place it between F and 2F, you're going to check from F to 2F, if it is 10 centimeters, then between F and 2F, halfway between F and 2F, it will be 5 centimeters between F and the image, or 5 centimeters, 5 centimeters between F and the object, or 5 centimeters between the object and 2F. So between simply means halfway between F and 2F. So if I say I am placing an object between F and 2F, I am simply saying to you, I am placing it halfway between F and 2F. Then you are not going to complicate this. You will just use 2 light rays altogether, so that you show us the transmission of the light ray through the convex lens. So the light from the object, the first light that you will show us, is the light that moves from the object and it goes through the optical center, and it goes all the way, and it does not change direction. Please remember that. So the first light ray that will show us is the light from the object. Remember, the object will be giving you, the light will be coming from that particular object, and it will go through the optical center altogether, and it must not change direction. That is the first light ray that you will draw, and you will show us an arrow. If it doesn't have an arrow, then you don't get a mark altogether. And it must go through the optical center. How did you see the optical center? The optical center is halfway from one edge to the other edge. So you will check your lens. If this lens is 20 centimeters, then it means 10 centimeters will be halfway. So it will be at the center altogether, and you count it from the edges. And then if from this point to that point, let's say it's 4 centimeters, then halfway through is going to be 2 centimeters. So you check where you are halfway through the lens in terms of the edges, and halfway through the sides altogether. And where the points meet, that is your optical center. And then you will show another light ray. The other light ray must be this light ray that I'm indicating to you there. And this light ray is parallel to the principal axis. Remember, this line there represents the principal axis. So this light ray is parallel to the principal axis. So it will go parallel to the principal axis, and then when it gets there to the optical axis, it is refracted. In other words, it bends. And when it bends, you must make sure that it bends and it goes through the focal point. And it goes through the focal point all the way. You just extend it. You extend it all the way up until it meets up with this light ray that passed through the optical center. So there's the light ray from the object through the optical center up to there. The light ray that is moving parallel to this principal axis. At the optical axis, it refracts through the focal point all the way. And at that point, you can see the two rays are crossing. And that is where the image is going to form. And then you will show us the image. Obviously, the image will be from that point, from the principal axis, all the way up to there. So you will show us through a line altogether. Preferably, use a line that is not broken. Like, do not use a broken line. Do that and then indicate with an arrow. And the arrow must be right where the two lines cross each other altogether. And that will be the image. And the arrow, you can see it is facing downwards. And then we say, okay, that is the image. Now, I want you to check something there. You see, when we deal with light rays, you have to indicate the direction of the light ray. That is why I've shown you the direction there, and I have shown you the direction there. You see, it was going in that direction because it was parallel to the principal axis. This is the principal axis. So this is the light ray parallel to the principal axis. And there I am showing direction again to show that the direction has changed. It has bent. But there the direction is always the same because it goes through the optical center without changing direction. So always know the light ray through the optical center is not changing direction. And that will be the image. Now, you see with the convex lens, it can form images that have different properties. And it depends on where that particular object was placed. But according to this one, my dear learners, what we can see about this image is that this image, number one, is larger than the object. Can you see the size of the arrow there? Is smaller than the size of the arrow of the image. So the image is larger than the object. Number two, the image is inverted. The arrow is going downwards. It's not going upwards. So the image is inverted. It's facing down altogether. So it is inverted. If the image was like this, then we would say it is upright. So the object is upright, right? The object is upright, but the image is inverted altogether. So those are the images, rather the properties of the image. Again, my dear learners, what you can see here is that the image is real. And how do you know the image is real? Because a convex lens, the light rays meet. And if the light rays meet, then the image is going to be real altogether. And this is essentially how we would have marked you. You would have shown the ray from the object parallel to the principal axis, which is this one. You would have shown the ray drawn from the object through the optical center of the lens, and it does not refract. It doesn't change direction. Then the ray from the object parallel to the principal axis through F after refraction or the ray from the object through F parallel to the principal axis after refraction. So we are basically talking about that light ray there altogether. So it was the one parallel to the principal axis, and then this one, you would get a mark. And then two rays cross beyond 2F. So the image was formed way beyond 2F, because that is 2F, but the image was formed beyond 2F. And the image was then indicated by an inverted arrow. And those are the properties of, rather, how we would mark you for this one. Then we have a concave lens. With a concave lens, my dear learners, let us say we place an object again between F and 2F. Remember, my dear learners, this line there, it's still your principal axis. Your F, it's still the focal point. And then this point there, it's still the optical center. And this broken line still represents the optical axis. Are we together? Now, we know a concave lens is diverging in nature. Now, if it is diverging in nature, it means the light rays will never meet. They don't meet, so they diverge. So we do the same thing. The first light ray, my dear learners, will be from the object. It's still placed between F and 2F. By now, you know what that means. It's halfway between F and 2F. So it will go through. The first light ray will be the light ray from the object going through the optical center. And we said it doesn't change direction. That will be the first mark. The second mark is for the light ray that goes parallel to the principal axis. So it's the principal axis. So this light ray is moving parallel to the principal axis. And then when it gets to the optical center, what does it do? It diverges. That becomes another mark. Remember, it won't go through the focal point altogether. It will then diverge. Then what do? We then want to see how the image will form. So we will take this light ray that diverged, and remember, you must extend it. So you extend it, and at the point after extending, you see there, that extension meets up with this light ray. That is where the image is going to form. So it's not going to form there. You don't extend it. The image is not formed where the extension ends. The image is formed where the extension ends, right there. Are we together, my dear learners? So that will be the image. Now, this image, you will then show us with an arrow, and you can see that the image is definitely upright. So the arrow must go upwards. That will definitely give you a mark. Again, another mark there is actually given for the position of the object being between F and 2F. So you have followed an instruction, that would be a mark. And again, your image is upright. We talked about that, and that your image is smaller. So if I asked you about the properties of this image, you can see that the image there, it's actually upright. Secondly, the image is smaller than the object, and the image is virtual. Altogether, my dear learners. And that is essentially what you are going to be asked in terms of lenses. It's just that we can place them at any particular position. Altogether, remember that. And that is essentially the question that I'm saying to you, you would be asked. And this is how you can definitely go and practice your concave lens as well as your convex lens altogether. So this is essentially what I wanted to teach you for today. So remember to be able to deal with this type of questions altogether. And that is all I actually had for you today. Remember, this question is going to be, rather this section of the work is going to be plus minus 41 marks in your examination. Are we together? So prepare thoroughly, know your lenses, and be able to draw their transmission, the transmission of light, either through a convex lens or a concave lens. Then send me more questions to stemdigitalschool@africateamgeeks.co.za. Thank you for joining me for this particular lesson. I will see you tomorrow, same time, same place. Enjoy the rest of the evening. Goodbye.